Hello YouTube and welcome back. Alright, this is Calc Unit 6, Section 4, our last topic, how to find volume using washers and definite integrals. So, let's do that. So take a look at the homework set. Tonight is page 411, multiples of 4. Take a look at number 17. It's our last topic before our last take-home and our final. That's it. We are done. This is the traditional end of AB calculus or Calc 1 in college, where you're doing volume by disks and washers, and you're doing U substitution. All right, so let's do it. So consider the volume generated by revolving the region enclosed by y equals x squared plus 1. Okay, so let's graph that. Now, x squared plus 1, you know what y equals x squared looks like, right? So just shift it up 1. Oh, more or less. Okay, I don't like. That's not very symmetrical. Let's try that again. Here's 1, right? Let's pretend that's okay. So that's y equals x squared plus 1. And the line y equals x plus 3, which has a y-intercept of 3. And let's say this is a slope of 1. So this region here, if you revolve that around the x-axis, you get a weird shape with a hole in the middle. That's what's different today. How do you figure out that hole? All right, so this is what we're going to do. We're going to pretend it's a disk problem like yesterday. Pretend there's no hole. Say you're only dealing with the volume of revolution of the line. Let me call that say a green volume. So we write a Riemann hypothesis, Riemann rectangle, which is green, in thickness dx, as always, right? Why is that working? So here's your Riemann rectangle, in thickness dx, very thin, infinitesimally thin, but the height is the y value there, which is x plus 3. So now if you revolve that around the x-axis, you get a disk of thickness dx. But what's the radius of rotation? It's the y value, x plus 3. Okay, so that green volume is going to be pi r squared dx. dx is the thickness of the disk or the height of the cylinder. Think of it as a very short cylinder. All right, that's the green volume. Now, that's if there's no hole. Now, they took out this thing in the middle, which is a hole. Let me make it a blue volume. And I'm not going to draw the disk, but pretend there's a disk here when we revolve that vertical strip. If the strip touches the x-axis and it's perpendicular to the x-axis, when we rotate around the x-axis, there's no hole in the middle, that's a disk, right? So the radius of rotation is still the y value there, but now it's x squared plus 1. So you get pi r squared dx is pi x squared plus 1 squared dx. Okay, so that's the volume of the green disk, that's the volume of the blue disk. How do I get all the disks, all the volumes added up from here? I messed this up. Okay, hang on. Okay. So how do I get the volume from here to here? That we don't know. What's this x value here and what's this x value here? I don't know. Let's find out. It's the point of intersection of the two lines, two curves, right? So how about we do that down here somewhere? Well, let's do this over here. So when does x plus 3 equal x squared plus 1? Well, let's set this equal to 0 and factor if we can, or quadratic formula if we can't. 2 nice easy integers and multiply out to -2 and add up to positive 1. Negative 1, there it is. So x equals 2 or x equals -1. Okay, good. So I know what this x value is over here. It's -1. And this one over here is positive 2. Okay. So how do I get, if this is the volume of just one green disk, how do I add up all the green disks from -1 to 2? I do the summation, which is the definite integral, as you know, from -1 to 2. And the same thing with the blue stuff, from -1 to 2. And then that's the big volume is the green stuff, the little volume is the blue stuff, the little volume is over like whittling away. And so we're going to subtract those two volumes, and we're done. All right, so that's it. Now, so that's the setup. It's really a big disk minus a little disk. So it's sort of disks again, like yesterday. So this isn't really new. The setup is a little weird, but it isn't really that new. So how are we going to evaluate each of these volumes? What's the green volume? What's the blue volume? All right, let's figure out the green volume. So how about over here? The green volume is pi times the integral from -1 to 2 of x plus 3 squared dx. Now, you could FOIL that out if you want. But why don't we do it with U substitution? Remember, if it's x squared dx, you just write x cubed over 3 and you got the antiderivative. You're done. But if it's x plus 3 squared, it's something not just x, it's a chain rule. We got to do a chain rule backwards. So what's the inner function, what's the outer function? The inner function is x plus 3. The outer function is the squaring function. So let's give the inner function a name. I call it u. Then tell me what du dx is. Well, it's 1. Now, can you use that to figure out what dx is? Cross multiply. And it turns out that dx and du are the same. All right, so this isn't too bad. Wherever you see dx, write du. Wherever you see x plus 3, write u. But now the limits of integration are not -1 to 2 because those are x values. Take -1, plug it in here. That's your u value. So when x is -1, u is 2. Take your x equals 2, plug it into here, and you get 2 plus 3 is 5. And that's what you're doing. All right, so now it's easy. If you know that the antiderivative of x squared dx is x cubed over 3, you know the antiderivative of u squared du is u cubed over 3. And it's plus c if it's just the antiderivative, but we're plugging in limits of integration. 2 to 5 times pi. So what's the big volume? The volume of the big disk, the big disks, right, is the green strip that we drew. Okay, so let's plug in 5. Let's plug in 2. 2 cubed is 8. Let's subtract, multiply by pi, and you're done. Wow, that's crazy. So that's the big volume. Let me just check my work. So what is that? That's 117 over 3 pi, isn't it? And 1 plus 1 plus 7 is 9, a multiple of 3, so 3 goes into it 39 times. So it's 39 pi cubic units, whatever they are. So in the diagram, if this is 2 inches from the origin, right, that would mean then that the green disks add up to a volume of 39 pi cubic inches, right? Okay. All right, so let's finish this off. What about the blue disks? Let's add all of them up. All right. So the blue stuff looks like this. Pi times the integral from -1 to 2 of x squared plus 1 all squared dx. Now this is not what I would call a u sub, because what is the derivative of, if I call the inner function u equals x squared plus 1, what's the derivative of u? The u dx is the derivative of x squared plus 1 is 2x dx. Yeah, I don't have that in my problem. I don't have an x dx to play with. So this is not a u substitution. So what are you going to do instead? Make it easy. FOIL it out first. So x squared plus 1 times x squared plus 1. First times first. Outer times outer is x squared. Inner times inner is x squared. So 2x squared. Last times last is 1. Notice I'm not anti-differentiating yet. I'm just making it easy to do so. So this is going to be the volume of the whole. I guess the smaller disks. And they take a big green volume minus a little blue volume, right? So now we can differentiate, because this is just power rule. X to the 5th over 5 plus 2x cubed over 3 plus x evaluated from -1 to 2 and multiplied by 4. Okay. So plug in 2. So this is going to be pi times, plug in 2, plug in -1, and subtract the 2. Fundamental theorem of calculus. Excuse me. So plug in 2, and you get 2 cubed is 32 fifths. 2 to the 5th is 32, and 2 cubed is 8 times the 2/3 is 16 thirds, plus 2. All right, plug in -1. -1 to the 5th is -1, so -1 over 5. -1 cubed is also negative, so -2 thirds, and plug in -1. Okay. Now remember, how do you subtract? You never do. So we're going to be adding the opposite of all this stuff. Right? So what do you get? You're going to get 32 fifths plus 1/5 is 33 fifths. 16 thirds plus 2 thirds is 18/3. 2 plus 1 is 3. Okay, that's an answer. But what if we combine all the fractions? Common denominator would be what? 15? So multiply top and bottom by 3. Multiply top and bottom by 5. Multiply top and bottom by 15. And you get 99 plus 90 is 189 plus 45 is 234. Okay, so what did we get? We got that the green volume is a total of 39 pi cubic units. The blue volume is a total of 234 fifteenths of pi. Okay, and so what's the answer? The answer is the volume of this black region revolved around the x-axis is 39 pi minus 234 fifteenths of pi, which you could simplify a little bit, I guess, but there you go. And that's it, done. So these problems, when there's a hole in the middle, big this minus little this. Pi big R squared dx minus pi little r squared dx. And r here is usually a y value if we're revolving about the x-axis. All right, you can get more crazy with this. Next year, when you take AP Calculus AB or Calc 1 in college, you can get a little more crazy with this. You might be revolving around the y-axis and craziness, okay? So it gets a little more crazy than this, but this is sufficient for us. How do you check this? Can we check this on the calculator? Let's see if we get the same answer. All right, so go to the calculator. All right, so next year you're just going to have more time to play around with the stuff and get it down and understand the nuances and details that maybe we glossed over a little bit. Okay, so let's do pi times math 9. You can put the pi inside or outside the integral because remember that the derivative of a function times a constant is the derivative of the function times a constant. Same thing for antiderivative. So I can put the pi inside and then to differentiate it, put the pi outside and just multiply by 5 when I'm done. Now going from -1 to 2, because this doesn't do indefinite integrals or antiderivatives, just numerical integrals or definite integrals. And it's going to be the quantity x plus 3 squared. And, wait, could I do it this way? Could I just do x plus 3 and then go here and square it? No, it won't let me do that. Okay, so I take that back. Quantity x plus 3 squared. There you go. With respect to x. And this was the big blue area, which was, sorry, the big green area, which was 39 pi. Is that 39 pi? Let's see, 39 pi is same thing. Good. Okay. And then the other area, the green area, the smaller area that we're taking out in the hole, is similar. It's still pi. It's still a dx. It's still -1 to 1. And we're still squaring the radius, but the radius here now is, let's see, second insert squaring x squared plus 1. And that's 49.009-ish if you round it off. And the other one's 122.522-ish. Is that what we had? Didn't we have alpha y equals rational 234 fifteenths of pi? Is that the same thing? Yeah, so the answer is 39 pi minus 234 fifteenths of pi. All right. Or 122.552-ish minus 49.009-ish is the final volume of that black region revolved around the x-axis is 73.513-ish. Now I'm curious, what if I said 39 minus 134 fifteenths times pi, right? So that's an exact answer. Math bracket. And you could write 1/17 if you want, or 23.4 times pi. 1/17 times pi, same thing. All right, so our final answer was 117. So this equals 117 of pi, which is about, what the heck was it? Whoops, I lost it. What was the difference? 73.513. 73.51 cubic units, whatever they are. If it's, -1 inches from the origin and +2 inches from the origin, then this is 73.513 cubic inches, right? Or 117/5 of pi cubic inches. Or there's nothing wrong with writing 39 pi minus 234/15 of pi cubic inches. Yeah, okay, done. All right, so that's what the homework looks like. Most of it's for tonight. Same page, page 411. All right, hope that helps. There you go. So there's the whole kit and caboodle. That's it. All right, we're done. Have a nice summer, guys. Well, my next video will not be until September, so we're done. But the rest of the next couple of weeks is reviewing for the final and reviewing tomorrow for the last test. Okay, bye-bye, YouTube. Have fun.